is Dr. Shankaraiah from Department of Physics. Today I am going to discuss question bank on Module 1, Part B, second presentation. So the earlier 10 questions on Part B I have discussed in earlier presentation, and today I am going to discuss the remaining 10 in Part B, Module 1. So the 11th question in Part B is, what are Bravais lattices? Draw the Bravais lattices for orthogonal systems. Okay. So Bravais showed that there are only 14 possible ways of arranging the atoms, and these 14 types of arrangements only satisfy the condition of periodicity. And these 14 types of arrangements are called Bravais lattices. So the condition or constraint is that they have to satisfy the property of periodicity. Only then we call those lattices as Bravais lattices. Okay, so these Bravais lattices, 14 Bravais lattices are classified into 7 crystal systems: cubic, tetragonal, orthorhombic, monoclinic, triclinic, hexagonal, and trigonal. Okay, so yeah, then these are the 14. Draw the 14 Bravais lattices. Yeah, so these are the 14 Bravais lattices. Cubic there are 3, tetragonal there are 2, and orthorhombic there are 4. So 3 plus 2 5 plus 4 9, and then monoclinic 2 7 plus 9 plus 2 11 11 plus triclinic 1, trigonal 1, and hexagonal 1. So these are the 14 different types of Bravais lattices that are classified into 7 crystal system, naming cubic, tetragonal, orthorhombic, monoclinic, triclinic, trigonal, and hexagonal. Okay. So this is the answer to the first question, 11th question. The 12th question is, explain the 7 crystal systems based on interfacial angles and interatomic distances and mention the Bravais lattice structures for each crystal systems. Okay, so we need to explain 7 crystal systems based on interfacial angles alpha, beta, gamma, and interatomic distances A, B, C. And we have to mention also what kind of Bravais lattices that belong to. Okay. So these are the 7 crystal systems starting from triclinic, and we are here discussing about the interatomic distances or axial lengths ABC. So based on 7 crystal systems, and based on axial lengths are interatomic distances. This is also called as interatomic distances. These are A comma B comma C. And interfacial angles are interaxial angles, alpha, beta, gamma. So we are discussing the relation between these angles, interaxial angles, and axial lengths or interatomic distances for these 7 crystal systems, right? So first, a triclinic crystal system. So there are triclinic has only one type of Bravais lattices, that is primitive, or and only one type of triclinic system, and the relation between these axial lengths or interatomic distances is A is not equal to B is not equal to C, A is not equal to B is not equal to C, and alpha, beta, gamma are not equal to 90 degrees. So all these axes, crystallographic axes, are not perpendicular to each other, and the axial lengths are also not equal. A is not equal to B, X, Y, Z if you take. So the distance between 2 atoms along X is A, distance between 2 atoms along Y is B, distance between 2 atoms along Z is C. Okay, so these axial lengths along XYZ directions are not equal, and the angles between these axes alpha, beta, gamma are also not 90 degrees. So all these axes are not perpendicular to each other, and they are all having different lengths. That is triclinic system, and it has only one Bravais lattice. Second one is monoclinic crystal system, and this monoclinic crystal system has 2 different types of Bravais lattices. And and the relation between axial lengths or interatomic distances is A is not equal to B is not equal to C, but alpha is equal to gamma is equal to 90 degrees but not equal to beta. So all the axial lengths are not equal again for monoclinic crystal system, but two angles are 90 degrees. That means alpha xy axis are perpendicular to each other and yz axis are perpendicular to each other, for example, but z and x axis are not perpendicular to each other. Okay, so alpha is equal to gamma is equal to 90 degrees but not equal to beta. So that is monoclinic crystal system which has two Bravais lattices. Then orthorhombic crystal system. Orthorhombic crystal system has four different types of lattices, as I showed here. Orthorhombic has four different types of lattices. So yeah. So for there are four different types of Bravais lattices: face centered, body centered. Yeah. So simple, body centered, base centered, and face centered. Okay. So monoclinic also simple and base centered, and this is simple triclinic system. The relation between these axial lengths is for orthorhombic is A is not equal to B is not equal to C again, but alpha is equal to beta is equal to gamma is equal to 90 degrees. So we have started with the worst crystal system. That means in the sense that all the angles are not equal to 90 degrees and all the axial lengths are also not equal. Then we are going in a but the best crystal system, right? So yeah, then the tetragonal system. Tetragonal crystal system has two different types of Bravais lattices, right? Simple and body centered. Okay, so tetragonal has A is equal to B is not equal to C. So two of the interatomic distances along x and y are equal but not equal to the third one, and alpha equal to beta equal to gamma equal to 90 degrees. So that is tetragonal. Next one is cubic. Cubic has three different types of arrangements. So simple, body centered, and face centered. So P is simple cubic, one arrangement, and I is body centered cubic, and F is face centered. So wherever you see P, that is simple monoclinic, at simple triclinic, simple orthorhombic, simple tetragonal system. And wherever you see I, that is body centered. So body centered orthorhombic, and body centered tetragonal, and body centered cubic. Wherever you see C, that is base centered. Okay, base centered. C is base centered. Base centered. Okay. Yeah, so for a cubic is best, yeah, so it has more symmetry. A is equal to B is equal to C, and alpha is equal to beta is equal to gamma is equal to 90 degrees. That means all the crystallographic axes are perpendicular to each other and all the axial lengths are equal. Best. And hexagonal one has only one Bravais lattice, that is body centered. Yeah, and the relation between axial lengths is A is equal to B but not is equal to C. Alpha is equal to beta is equal to 90 degrees, but gamma is 120 degrees. So this is different. So here the angle between two of the axes is 120 degrees. So this is hexagonal crystal system. Coming to rhombohedral or trigonal, it has only one type of Bravais lattice. And the relation between the axial lengths is A is equal to B is equal to C. All the axial lengths are equal along three axes, and the angle interaxial angle is alpha equal to beta is equal to gamma is not equal to 90 degrees but less than 120 degrees. Okay, so these are the 7 crystal systems, and the relation between the axial lengths are interatomic distances and interaxial angles, and different types of Bravais lattice. How many Bravais lattices are there for each crystal systems, right? So there are basically 14 Bravais lattices. So one is triclinic, 1 plus 2 3, 3 plus 4 7 plus 2 9 plus 3 12 plus 1 13 plus 1 14. So there are 14 Bravais lattices that are classified into 7 crystal system, and these are the relations between the axial lengths and interaxial angles. So we have answered this question. So the next question is 13th question in part B. List the type of lattice arrangement in crystals. Explain them with neat diagrams. Okay. So how many lattice arrangements are there in crystals, and explain them with neat diagrams, right? So we know that there are 14 different ways of arrangements. So we can start here. We can write here that so there are 14 Bravais lattices. There are 14 Bravais lattices. are 14 types of arrangements of atoms. Types of arrangements. Arrangements of atoms. Okay. So these 14 types of arrangements of atoms, we know that these 14s are classified into again 7, right? So these 7 crystal systems we have discussed: cubic, tetragonal, monoclinic, orthorhombic, triclinic, or trigonal, right? So these 14 different types of arrangements we have to draw neatly. Okay. Yeah. Yeah, so these are the three for cubic: simple cubic, body centered, and face centered. Three. And there are two for tetragonal: simple and body centered. And there are four for orthorhombic: simple, base centered. So this is the base center. See, there is atom at the base and at the top. So base centered orthorhombic, body centered orthorhombic, and face centered orthorhombic. So there are 9 here. And then again, monoclinic has two different types of arrangements: so simple and base centered. 9 plus 2, 11. Triclinic 1, and trigonal 1, and hexagonal 1. Okay, so there are 14 types of arrangements of atoms in crystal, and this is we have shown all these 14 types of arrangements. Next, 14th question in part B is: prove that the FCC has the highest packing fraction than simple cubic and body centered cubic crystal. Okay, so we have to show the packing fraction is more for face centered cubic crystal. Okay, so we have to define what is atomic packing fraction. Atomic packing fraction is nothing but the fraction of space occupied by atoms in a unit cell is known as atomic packing fraction. So the remaining space which is not occupied by the atom is called as void space or free space. Okay, so atomic packing fraction is defined as a ratio of effective number of atoms in the unit cell to the total volume of the unit cell. Volume of the effective number of atoms in a unit cell to the total volume of the unit cell. So that tells us about the atomic packing fraction. So yeah, so atomic packing fraction, mathematically we can write it as Z into small v divided by capital V, where Z is the number of atoms per unit cell multiplied with the volume of the each atom. So if there are 2 atoms per unit cell in BCC, so 2 into volume of each atom. So suppose if you are taking spherical atoms, so what is the volume of the spherical atom? So 2 into spherical atom volume divided by the total volume of the unit cell will tell us about the atomic packing fraction. So atomic packing fraction for simple cubic unit cell we have calculated here. So Z is equal to 1 for simple cubic unit cell. Then volume is A cube. So A is for simple cubic unit cell, A is 2R, where R is radius of each atom. So 2R cube is 8R cube, and volume of each atom is spherical atom we are considering, so that is 4 by 3 pi R cube. So the atomic packing fraction is Z into V. So 1 into 4 by 3 5 R cube divided by 8 R cube. So we will get 5 by 6, which is 0.52. So atomic packing fraction for simple cubic lattice is 0.52. Coming to body centered cubic unit cell. For body centered cubic unit cell, number of atoms per unit cell is 2, and radius per body centered atom is 3 by square root 3 by 4 into A. So A is equal to 4R by square root 3. Okay, and we are taking spherical atoms, so volume is 4 by 3 pi R cube, and volume of the unit cell is A cube, so A is 4R by square root 3. So cube that out. So atomic packing fraction is Z into V, small v, divided by capital V. So we get 5 into square root 3 by 8. So which is 0.68. So for BCC, body centered cubic unit cell, the atomic packing fraction is 0.68. Then face centered cubic unit cell. So for face centered cubic unit cell, Z is 4. Number of atoms per unit cell is 4, and the relation between radius and interatomic distance is A by axial length is A by square root 2 root A by 2 root 2, or A is equal to R into 2 root 2. Okay, so we need A cube, so A is 2 root 2 into R whole cube. So atomic packing fraction is Z into V by capital V, where small v is volume of each atom, so that is 4 by 3 5 R cube, and V is volume of each unit cell, so that is A cube. Okay, so by doing Z into V by V, we get 5 by 3 root 2, which is 0.74. So the atomic packing fraction for FCC unit cell is 0.74. So we have calculated the atomic packing fraction for simple cubic unit cell, body centered cubic unit cell, and face centered unit cell, and we found that simple cubic unit cell as 0.52 atomic packing fraction, and body centered cubic unit cell as 0.68, and a face centered cubic unit cell as 0.7. So from these calculations, we proved that the face centered cubic unit cell is having more atomic packing fraction, or is more closely packed structure of the atoms. Okay, FCC is the more close packed structure. So that is what they have asked. Prove that FCC has more highest packing fraction, and we have proved that. The next question: what are lattice planes? Obtain the interplanar separation of simple cubic lattice. Okay. So what are lattice planes? So we know that crystal lattice may be regarded as an aggregate of set of parallel and equally spaced planes passing through the lattice points, and these planes are called lattice planes. Okay. Each lattice has many parallel planes, and these parallel planes are called lattice planes, and these are all equally spaced parallel planes, and the perpendicular distance between the adjacent planes is called interatomic distance. Suppose if I draw the so lattice, and these are the planes all these parallel planes, and the distance between these parallel planes is called as interatomic distance. So a given space lattice may have infinite set of lattice planes, each having its characteristics interplanar spacing. In a crystal, the geometric location of a plane is not important. Okay, so the interplanar lattice planes are nothing but the parallel set of parallel planes that are obtained by joining the lattice points, and the distance between any two lattice planes is called interplanar spacing. So we need to obtain the equation for interplanar separation. So to derive the equation for these interplanar spacing or interatomic distance, interplanar spacing, we are denoting it by D, that is the distance between successive lattice planes is called as interplanar distance. And to derive this interplanar distance, we need axial lengths as well as Miller indices as well as axial lengths, right? So, and we are going to derive this interplanar spacing or interplanar distance for cubic system. Okay, so to derive this interplanar distance, we are taking two parallel planes. So this ABC is one parallel plane, and another parallel plane is here, for example. So this is one planes, right? And this is another plane. So we are going to calculate the distance between these two parallel planes. Okay, so to derive that, I am considering one family of parallel lattice plane, which is ABC. Now, so I am going to write the Miller indices. HKL are the Miller indices for this plane, and intercepts are A by H along X. This is X axis, so A by H along X axis, and B by K along Y axis. So this is Y axis, and the intercept is B by K, and C by L is along Z axis. Okay, so this plane, the plane ABC, is cutting the XYZ axis. So this is the intercept, so that is A by H, and this is the intercept along Y, so that is B by K, and this is the intercept along Z, that is C by L. So these are the intercepts, and HKL are the Miller indices of this plane. Okay, and to calculate the interplanar distance, we need to take another plane. So this is the plane that is passing through the origin, and the distance between these two planes is the interplanar distance. Okay, and this to derive this interplanar distance, I am going to consider the normal to this plane. So the normal to this plane is ON. ON is the normal to the plane, and this normal, the length of the normal is D, that is the interplanar distance between this ABC and another plane that is passing through the origin. So if I derive the equation for D, which is the length of the normal, then I am done with the derivation of interplanar distance. Okay, so this normal is making an angle alpha with X axis, making an angle beta with Y axis, making an angle gamma with Z axis. So these are the angles that made by the normal with XYZ directions. Once I know these angles made by this normal, I can write down the direction cosines. Okay, so I can write cos alpha from this triangle. Okay, from this triangle OAN, I can write cos alpha. Cos alpha is adjacent by hypotenuse, so ON by OA. So ON is D and OA is A by H. Similarly, I can write cos beta also. So cos beta, so this is the normal and this is cos beta. So cos beta is adjacent is ON divided by OB. ON is D and OB is BK. Similarly, I can write the cos gamma. So cos gamma is this. So this is OD and this is cos gamma. So cos gamma is adjacent by hypotenuse. So adjacent is ON and hypotenuse is OC. So D by C by F. So once I write down the direction cosines using these triangles, I know that the sum of the squares of the direction cosines of a line must be equal to unity, and so using that trigonometric relation, I am writing this cos square alpha plus cos square gamma plus cos square beta must be equal to 1. So I have substituted cos alpha, cos beta, cos gamma. So cos square alpha is this, cos square beta is this, and cos square gamma is this. That must be sum of these squares of this must be equal to 1. And using this, I got this. So I can take out this d square common. So I got h square by a square, k square by b square, and l square by c square. So then d will be so from this, after this equation, I get d will be 1 by square root h square by a square plus k square by b square plus l square by c square. Okay, so if I take a cubic system where axial lengths are equal, a is equal to b is equal to c, I get a here and all these abc will go away, right? So for a cubic system, this equation will be simplified to this equation. So d will be a by square root h square plus k square plus l square. So this is the derivation for interplanar distance for a cubic system. So we have answered the question what are lattice planes, and we have derived the equation for interplanar distance. So the 16th question is differentiate simple cubic, body centered cubic and face centered cubic structures based on coordination number, nearest neighbor distance, atomic radius and atomic packing fraction. Yeah, so this is a tabular form for these different parameters of simple cubic, body centered cubic and face centered cubic unit cells, right? For example, volume is A cube for all these three different unit cells, whereas atoms per unit cell, Z, atoms per unit cell is 1 for simple cubic, 2 for body centered cubic and 4 for face centered cubic. Atomic radius is A by 2 for simple cubic, square root 3 by 4 into A for BCC, and A by 2 root 2 for face centered cubic. Coordination number is 6 for simple cubic, 8 for body centered and 12 for face centered. Atomic packing fraction 0.52, 0.68 and 0.74. Void space 48%, 32% and 26%. Void space is nothing but the empty space. Okay, 1 minus atomic packing fraction will give you the void space, percentage of void space. Density is Zm by Na into A cube. So Z is 1 for simple cubic. So 2 for BCC and 4 for FCC. And nearest neighbor distance is nothing but 2 into radius of each atom. So 2 into radius of each atom. So 2 into A by 2 will be A. 2 into A square root 3 into A by 4 will be square root 3 into A by 2 for BCC and A by square root 2 for simple cubic lattice. So we have discussed different parameters for simple cubic, body centered cubic and face centered cubic. So we have answered the question. What are lattice planes? Explain the concepts of Miller indices. Obtain Miller indices for a plane making intercepts PA, QB, RC with crystallographic axis. Okay. So we have discussed what are lattice planes. Lattice planes are nothing but the set of parallel planes in a lattice. And these equally spaced planes passing through the lattice points are lattice planes. And the distance between any two of the lattice planes is called interplanar spacing. Okay, and Miller indices are used to find out the position and orientation of any lattice plane in a crystal. Okay, to find out the position and orientation of any lattice plane in a crystal, we need some smallest integers, and those integers are called Miller indices. And we need to derive the equation, obtain the Miller indices. Okay, so these are some of the rules to obtain Miller indices. First, we need to write down the intercept. Once we write down the intercepts, we are going to write down these intercepts in terms of base vectors. So PA, QB, RC as the base vectors of these intercepts, okay, along XYZ directions. Okay, once we write down these intercepts in terms of base vectors, we are going to find out the reciprocals of these intercepts, And then once, if you have any fractions in the reciprocals, 1 by p, 1 by q, 1 by r, if these are the reciprocals of the intercept, then we are going to multiply these reciprocals of the intercept with the least common denominator, right? So, and once we multiply these reciprocals of the intercept with the least common denominator, we are going to find out the set of smallest integers, which are called as Miller indices. So these p, q, r, which are the base vectors, all right? So p, a, q, b, r, c are the base vectors. So when we multiply with the least common denominator d, we get d by q, d by p, which I defined as h, and d by q, which is I defined as k, and d by r, which I defined as l. So these h, k, l, putting parentheses without commas, are called as Miller indices. Okay, so these yeah, so as they asked, obtain Miller indices for a plane making intercept pa, qb, rc. So if I take the plane, then I am taking the intercept and I am finding out these Miller indices with these base vectors pa, qb, rc. Okay, and hkl are the Miller indices. Define space lattice and explain the concept of space lattice for a two-dimensional array of infinitesimal points. Also explain the concept of basis and relate. Okay, so we need to define what is space lattice and how do we obtain this 2D array of points, 2D space lattice, and what is a basis, and we need to connect it. Okay. So space lattice is nothing but a three-dimensional array of points, and in which every point is surrounding identical to the every other point. Okay, so space lattice is basically a three-dimensional array of points, and in this array of points, if you sit at any point, at any lattice point, the surrounding should be same as at any other point. Okay, so that is what is space lattice. The surroundings must be identical to every other point. Okay, so yeah, so then how do we generate this space lattice in two dimension? We are going to use translation operation. Okay, so we are going to use the translation operation. Using this translation repeatedly in two dimension, we are going to generate the two-dimensional array. Okay, so yeah, so let us see how do we obtain these two-dimensional array of points. Okay, so first we are going to start with an arbitrary point and use this translation operation to generate a point of this is the lattice point we have generated using the translation of t1 along x direction. Okay, so if I use the translation operation for this point, again I am going to generate another lattice point at a translation of t1 again. If I apply this translation to this point, I am going to generate this point of a translation t. So using this repeated translation along x-axis, I have generated a row of points. Now from this row of points, I can use the repeated translation to generate another row of points along y direction. So this is y. Okay, so from this point again I can generate row of points using repeated translation. From this point I can generate another repeated row of points. Okay, so another row of points using repeated translation along translation of t2. If I join these points, I am going to get a plane of points in two dimensions. So this is a two-dimensional space lattice that is generated by translation operation that is used repeatedly along x direction and y direction. Okay, so this is how we generate the space lattice in two dimensions. Okay, next we are going to define what is the basis, right? And we are going to relate relate the space lattice and basis. A space lattice is a mathematical abstraction. We do not have any understanding of this lattice because there are just lattice points, right? So if we attach, so the group of atoms that is associated with every lattice point is called basis. To get an understanding of this lattice, we need to attach one atom or group of atoms to each lattice point. Only then we get a physical understanding or physical picture of this lattice, right? So basis is very important to define a crystal from a lattice. Okay, so basis is nothing but a atom or a group of atoms that is attached to every lattice point, and the constraint is that these spaces must be identical in composition, arrangement, and orientation. Okay, so if you are attaching a atom or a group of atom to each lattice point, these must be identical in composition, arrangement, and orientation, so that they satisfy the constraint of periodicity. Okay. Now, lattice plus basis. You have generated a two-dimensional array of points. So space lattice in 2D. So this is the space lattice in 2 dimension, and then you have attached a basis to each lattice point. So lattice plus basis will give you a crystal structure. So for example, I am attaching sodium atom and chlorine atom to each lattice point, for example. So I have a NaCl crystal, right? So lattice plus basis will give us actually the crystal, and that is physically understood. Okay, so we have answered the question. The 19th question in part B is explain the terms coordination number, nearest neighbor distance, atomic packing fraction, and atomic radius. Okay. So coordination number is nothing but the number of nearest neighbors of an atom. Okay. Number of nearest neighbor atom is called as coordination number, and this is 6, 8, 12 for simple cubic, body centered cubic, and face centered cubic atoms. And atomic packing fraction is the fraction of space occupied by atom in a unit cell. Okay, and we have defined this, and atomic packing fraction is 0.52 for simple cubic, 0.68 for body centered cubic, and 0.74 for face centered cubic unit cell. Okay, so this is coordination number and atomic packing fraction. And then atomic radius. So atomic radius is obtained, the relation between the apparent size of atom and edge of the unit cell can be determined where one atom is attached to a lattice site. Okay, to derive or to obtain the atomic radius of atomic radius, we need to find out is direction. We need to find out a direction along which all atoms are in contact. Okay, to find out the radius of atom, we need to find out the direction in which the atoms are in contact. Once we find out the direction along which the atoms are in contact, then we can find out the radius of atom using some simple geometry. Okay, for a simple cubic unit cell, the radius of atom is a by 2. For BCC, radius of atom is square root 3 by 4 into a. For FCC, the radius of atom is a by 2 root. Okay, so this is radius of atom in simple cubic, body centered cubic, and face centered cubic unit cell. To find out the radius, we must know the direction along which atoms are in contact. Once we know that, then we can find out the radius of each atom. And the nearest neighbor distance is the distance between the centers of two nearest neighbor atoms, and we can obtain the nearest neighbor distance as 2 into radius of atom. If you know the radius of atom, multiply this radius of atom with 2, then we are going to find out the nearest neighbor distance. Okay, so for simple cubic atom, nearest neighbor distance is 2 into r, so 2 into a by 2, so that is a. For body centered cubic, 2 into square root 3 by 4 into a, so that is square root 3 by 2 into a. For FCC, 2 into radius of atoms, 2 into a by 2 root, so 2 cancel, so a by root 2 is the nearest neighbor distance. For simple cubic is a, body centered cubic is square root 3 by 2 a, and face centered is a by square root. Okay, so we have answered the question, right? Nearest neighbor distance, atomic radius, coordination number, and atomic packing fraction. So last question in part B is define atomic radius and nearest neighbor distance and obtain the relation between atomic radius and interatomic separation for simple cubic, body centered cubic, and face centered cubic. Okay, so atomic radius, we have discussed. To find out the atomic radius, we need to find out a direction along which atoms are in contact, and we have just now discussed the atomic radius r is a by 2 for simple cubic. A is for simple cubic. A by 2 for simple cubic, and square root 3 by 4 into a for BCC, and a by 2 root 2 for FCC. Just now we have discussed this atomic radius. And then the nearest neighbor distance is distance between the centers of two nearest neighbor atoms, and that is obtained by multiplying the radius with 2. Okay, so just now we have discussed this also. And the other parameters is that if you know the nearest neighbor distance and atomic radius, we can obtain a relation between this atomic radius and nearest neighbor distance, right? So yeah, so this is the atomic radius for simple cubic, body centered cubic, and face centered cubic. And we know that nearest neighbor distance is 2 into atomic radius. So 2 into atomic radius is a. The at a nearest neighbor distance will be a for simple cubic, because 2 into a by 2 will be a, and 2 into a square root 3 into a by 4 is a square root 3 a by 2 for BCC, and a by root 2 for FCC. Okay, so if you know the radius of atom, we can find out the nearest neighbor distance using this relation. 2 into radius atom is actually defined as nearest neighbor distance. Okay, so these are the some of the textbooks and references which I have used. To summarize, in this presentation I have discussed the question part B, long answer questions of module 1. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.